Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will study scalar, but mostly we will study vector fields. What is this scalar field? What is a vector field? Before that, let me ask you a question. What is a signal? We know that if I have a circuit, okay, maybe some complicated circuit, but for now just imagine that there is a simple RC circuit, and this RC circuit is connected to a signal generator, and we connect an oscilloscope across the capacitor. Well, we can't connect an oscilloscope across the capacitor, so this is actually a virtual oscilloscope that I have connected. And if the voltage is changing with respect to time, the oscilloscope would also show us what is the voltage change that is happening across this capacitor. So we give a name, a special name for quantities that vary with respect to time. We call them as signals. Although signals can also be used to describe variations of a quantity with respect to position or with respect to anything, it is in general understood to be a quantity that is varying with respect to time. In electromagnetics, we have seen situations where a voltage changes with respect to time. Consider the familiar example of a transmission line problem. So let the transmission line be terminated with some impedance, and then let us say we connect a certain voltage generator to this transmission line, and if I keep an oscilloscope, or if I look at what is the voltage at this particular point on the transmission line, this voltage will be changing, and that would be corresponding to a signal, which would be the voltage signal, or this quantity would be a voltage quantity, right. Now I also know that on a transmission line, voltage at a point, let us call this point at this cross point, will not be the same compared to a voltage at this square point, because the voltage along the transmission line will vary. And if this is not a signal generator, but this is a battery connected to the transmission line at some t equal to 0, then you can see that the voltage distribution along Z will not exactly be the same as the input voltage. The voltage at the point X will be different compared to the voltage at point which is denoted by the square, and then the voltage will be different at the load side, right. So these quantities, if you were to freeze time, essentially this voltage is not changing, the battery is not changing with respect to time, but if at a constant time instant that I consider the voltage distribution along the transmission line, I might see something like this. The voltage at this point will be different, the voltage at this point will be different, the voltage at this point will be different, right. So if I freeze time, then the voltage at different points on the transmission line also is a function of the position at which I am measuring the voltage. So the quantity that I am looking for is something that is varying with respect to the position on the transmission line, and since we know that any position can be considered or represented by a vector, what we actually have is some quantity which is varying in terms of the position vector. So at different position vectors you have a different value for this particular quantity, and the quantity that we were considering was the voltage. So what we had considered was a quantity that was varying with respect to Z when the time was considered to be some constant time t equal to t naught. So we have one example of a signal which represents a quantity such as a voltage, current or power or whatever that is changing with respect to time, and then we have another quantity. In this case it is the same quantity, except now the quantity is dependent not only on time, of course, because things are changing with time, but it is also changing with respect to the position or with respect to the position vector. Z can be associated with a particular position vector. So what we have is a quantity that is varying with respect to position. You can even imagine scenarios where this quantity, whatever that quantity that we are considering, could just be a function of position. So if, for example, I take measurements on my body, I take my temperature at different points on my body and then graph that one. So this is my body, let us say this is the one that I am looking at, these are my legs and these are my hands, and if I look at the temperature at this point, the temperature at this point, the temperature here, the temperature will not be the same, the temperature at different points of my body will be different at different points. So what we have is an example of a quantity that is varying as a function of position, and such quantity is called as a field. In both examples that we considered, that is in the transmission line example that we considered as well as in the temperature of the body that we considered, the quantity that was varying was just a number, right? So you don't specify temperature and then say temperature in the direction of 30 degrees with respect to north. You just say that it's just a number, 30 degrees Celsius, 31 degrees Celsius, 32.3 degrees Celsius is just a number, and this number, as we know, is what is called as a scalar. So what we have, temperature at different points on the body as a scalar field, because it's a field because it is varying with respect to the points on the body. So it's varying with respect to the position, and in the case of a transmission line, the quantity that we were interested was a voltage. Again, voltage is a quantity that is scalar, because you don't say voltage at 30 degrees with respect to north. Voltage is also a scalar, and that is also an example of a quantity that depends both on z and time, right? In case you freeze time at say some t equal to t naught, then this is an example of a scalar field. So we have a correspondence of a quantity that is varying with respect to time, we call it as a signal, and then we have a quantity that is varying with respect to position, we call it as a field. Of course, these fields can be scalar or vector. In the case that we considered, we have only considered the scalar fields, which require just a number to be specified at every point in space and possibly in time as well. To come back to the electromagnetic example, let me take some charge and then throw this charge at different points, right? So I distribute the charge on a piece of paper, okay? So some places the charge density will be high, some places the charge density will be low, and the way these charge densities, the charge density or the charges are distributed on this piece of paper forms a scalar field. So if I denote the charge density as rho, and then this is the surface charge density, we will talk about all these quantities later on. So if I have this scalar quantity which I denote by rho s, this will be a function of 2 points x and y. Alternatively, I can write this as rho s as a function of capital R, where capital R is the position vector of this particular point on the piece of paper, which is x hat plus y hat, as we have seen in the previous class. So this is an example of a scalar field. So please note the notation. At every point, at every position vector, it's as though you pinned a particular number, and that number is the quantity that is scalar field. How might a vector field look like? Suppose I take the same charge distribution out there, right? And I know that around charges there will be electric field. This is something that we know from our high school physics classes, that surrounding a certain charge distribution will be the electric fields, and we know that electric fields are not just a number, but they have to be associated both with a number as well as a direction. You don't say electric field is 10 volt per meter. People will immediately ask you what is the direction of the electric field, right? So at different points the electric field direction will be different. You can also imagine that the amplitude of electric field to be different. As you move away from the charge, the amplitude will actually drop. So it will be larger nearer, and then the amplitude will drop according to what Coulomb's law that we already are aware of. But the point is, at every position vector R, I can associate a vector itself, right? So I have a vector associated at every position vector. This corresponds to a vector field, okay? We further can have a situation where this vector field is changing with respect to time. How might I obtain that? I take this charge distribution and then I shake this charge distribution, right? I make this, take it into a box and then just shake the box, and so the charges which originally here, they might just be displaced, and correspondingly the electric field directions will also change, right? It will not change immediately, but it will act after a certain small amount of delay, which we will talk about later. But the point is that the corresponding electric field also has changed, and if I keep doing this with respect to time, what I have generated is a vector field which depends on both the position at which you are measuring this vector as well as with respect to time, because of the shaking of the charge phenomenon. So this is a vector time varying field. You can have a time invariant field such as this case E of r, and if E of r is further dependent on time, then what you obtain is a time varying vector field. So you can have fields which are time variant and time invariant. So this is all about a scalar field and a vector field, okay. Now let us see what kind of operations we can perform on these fields and what kind of operations are important for the study of electromagnetics, okay. The goal will be to understand these vector fields and the corresponding calculus that is associated with these vector fields in order to appreciate Maxwell's equations, which form the basis of this electromagnetics the entire subject of electromagnetics. With that goal, let us look at what kind of calculus that these fields will obey. In our study, both scalar fields and vector fields will be important. Let us first look at a scalar field. Okay. So, I have a scalar field and I will use the Cartesian coordinate system to develop most of the relationships here. The relationships with circular, cylindrical and spherical coordinate systems are slightly more complicated. So, I will not develop them directly, but you can look at the textbook for the expressions, okay, to understand more about that one. And you can also look at some of the exercises where we will derive these relationships for other coordinate systems. So, purely out of my convenience I am using Cartesian coordinate system, but there is coordinate free interpretation of all these vector calculus operations, vector field calculus operations that we are going to perform. With that kind of a caveat in mind, let us look at a scalar field which we denote it by some f of x, y and z, right. I could of course obtain an equivalent description of f with a position vector r, but let us keep it here as f of x, y, z just to show you the Cartesian coordinate axis that I have taken. Okay. Suppose I have this function, I know the value of this function at a certain point at x equal to x naught, y equal to y naught and z equal to z naught. Okay. In other words, at a certain position vector r equal to r0, I know what is the value of this function f. Now, if someone asks me what is the value of this function f, the scalar function or the scalar field at x0 plus dx, at y equal to y0 plus dy and z equal to z0 plus dz. These values dx, dy and dz let us assume to be very small, so that I am not considering a point that is very far away located from x0, y0 and z0. It is actually a pretty close point, and the answer to this question, what is the function at this point, the answer to this question is given by Taylor's series, right. So, f of x is given by f of x0 plus x minus x0 into f prime of x0 plus and so on. If I retain only the first two terms, then I know how to write this f of x at x naught plus dx, y naught plus dy, z naught plus dz. Okay. And that value is given by approximating this one with Taylor series with only first term involved. This is given by f of x0, y0 and z0. This is something that I already know because that is the value that I already have measured and that is available with me. So, this plus the partial derivative of f with respect to x multiplied by the change in delta x itself. When you evaluate this partial derivative, you have to assume of course that y is y naught, z is z naught. Okay. And then you have the other contribution because of the change in the y direction. So, that would be del f by del y, delta y. Again this del f by del y should be evaluated such that x is x naught, z is z naught, and finally you have a contribution because of the partial derivative of f with respect to z evaluated again at x equal to x naught and y equal to y naught multiplied by delta z. Okay. Or rather in this case delta x is dx, delta y is dy and delta z is dz. So, let me rewrite all that. Okay. So, this is actually dx, dy and dz. You see that the change in the value of the function, which we can denote as delta f, this delta denoting the change in f given the value of f at x naught, y naught, z naught is simply given by del f by del x into del dx plus del f by del y into dy plus del f by del z into dz. Why do I need to take partial derivatives? Because f is a function of x, y and z. Okay. So, it is not just a function of one particular variable, it is a function of more than one variable, therefore, it is the partial derivative that needs to go in. And when I am evaluating del f by del x, that is partial derivative of f with respect to x, I have to keep the other two coordinates constant. The other two coordinates are y and z and they have to be kept constant. So, notice the way that we have written here is that you have partial derivatives, okay, multiplied by the change. Now, let us actually draw some pictures. Suppose I go back to this three-dimensional picture x, y and z and locate this point as the point r0. r0 is the point where I already know the function, and now I have considered a new point which I can call as r0 plus dr, right, where this dr is this small displacement vector which is given by dx x hat plus dy y hat plus dz z hat, right. So, if I go along direction x by a quantity dx, along y by dy, along z by dz, I am actually going from one vector which is the position vector at r0 to the new position vector at r0 plus dr, something that we have already covered here. Now, these two equations, if you look, then you might come up with a very interesting way of combining the equations, okay. And the way I combine the equation, you can observe here, I will first define vector associated with this partial derivative. So, I will call this as x hat del f by del x plus y hat del f by del y plus z hat del f by del z, right, all these partial derivatives being evaluated at the point r0, and then I take a dot product of this with respect to the displacement vector dr, which is dx x hat plus dy y hat plus dz z hat. The net result is the same because x dot x will give you del f by del x dx plus del f by del y dy, because you have y dot y, x dot y and x dot z are 0, similarly y dot x and y dot z are 0, and so on, right. So, what I obtain is the same expression, but what I have done is to define a vector, okay, and I call this vector as gradient of the scalar field f, okay. So, I call this as the gradient of the scalar field f, okay. This is connected, or this is dot product, or you have to take the inner product of this one with the corresponding displacement vector dr. And it is one of the conventions that instead of talking about the displacement vector dr, we talk about the change of a function along a particular line, and therefore we talk of the line element dl. Remember from the Cartesian coordinates that dl was the line element that we had picked, which was a vector line element, and this is given by dx x hat plus dy y hat plus dz z hat, right. So, you put in the remaining term over here. So, what you have seen is that if I pick up any direction, as long as the direction is reasonably small, then the change in the function, so I know the function value here at some position r0 and along this particular line, so let me draw that one in a red color. So, along this line element, the corresponding value of the function f of r0 plus dl, right, dl being the line element, I can obtain if I know the corresponding value of the gradient. And we have a special notation for this particular quantity which we call as the operator. We call this as the del operator. The reason for this calling this as a del operator is very clear, because these are only partial derivatives. Only this will make sense only when we take this and operate it on some quantity. In this case, we operate this quantity on the scalar field f in order to obtain what is called as the gradient of f. And this gradient of f is a vector quantity which can be used to dot with any other quantity, and the way we denote this entire thing that is in the brackets is by writing the inverted triangle and calling this as a nabla or the del operator. So, this is an example of one of the vector calculus or the operation that you are going to do with the scalar quantity called as the gradient. Let us look at an example, a numerical example, and then discuss what is the importance of this one, okay. So, let us say I know that f of x y z, is given by some 17x minus 2xy by z plus y square z cube, okay. This is some function that has been given to us, and we want to find out what is the gradient of this. The gradient of this is of course from the above formula that we already know. So, is that x hat del by del x plus y hat del by del y plus z hat del by del z operating on the scalar field f, which I have already given here. And what I will do is I will just give you the value of this del f at 2, 0 and minus 1. So, I will leave this as an exercise. You just have to complete these partial derivatives and evaluate these partial derivatives at 2, 0 and minus 1, and the value that you are going to get will be something like 17 x hat plus 4 y hat. As a result, this is a vector. We already know that this is a vector. Okay. So you might ask, what exactly are we doing here? I mean, why did I introduce a gradient operator? Observe something that is very interesting. The change in the function, which is given by the symbol that, you know, it's a proper triangle delta of f, as you move along a particular line, is given by del f dot dl. Now I know that this del f dot dl is a vector or is a dot product. So I have the magnitude of del f, right, which is a vector now, and then I have the magnitude of dl vector, and then cos of theta, where theta is the angle between. So let us say this is delta f, and let us say this line is the angle dl, or rather this line is dl, and this angle theta is the angle between these two quantities. If you move along the direction of delta f, cos theta will be equal to 1, and then what you obtain will be the maximum change, right. So the function undergoes maximum change if you move along the direction of the gradient, for which, you know, cos theta will be equal to 1. So this will happen when theta equal to 0, so that cos of 0 will be equal to 1, and the maximum change if you move a unit of dl is given simply by taking the magnitude of the gradient and then multiplying it by the magnitude of dl. This is of course just the magnitude, right. And if you move in the direction where the function is actually constant, then theta is equal to pi by 2, then delta f change, okay, that delta f change will be equal to 0, because in that case theta will be equal to pi by 2. To give you more understanding of that one, let me give you a simple picture out there. Imagine that I have this, you know, surface, palm of my hand, and I place this particular object. Okay, this is not a very nice object, okay, but let me place this object. Now what I do is I take a needle, okay, and I mark the needle here, okay, I mark the needle and then I paint some ink on the needle, and then I push the needle onto this, okay. I push the needle until it hits my palm. Of course it will be a little bit of a pain for me, but if I am able to withstand that one, then I pull the needle back. So as I push it and pull it back, I know that if I have a colored needle and let us say that color is removed from this object, you can imagine a potato for example, okay. So you can imagine a potato being kept on a nice, you know, surface over here, and then you plunge in the needle and then remove it, and whatever the marking that you would see on the, you know, this ink is gone. So that ink would represent the height of this particular object with respect to this flat surface at that position. So I have placed that object here. So at this point I plunge in the needle, pull it back, I know what is the height. So I can actually create at different points, you know, I can measure this needle and then create a height, and you can see here that the object is curved a little bit. So the height that you are going to measure at this point will be different from the height that you are going to measure at this point. In fact, we call this in the topography classes that this surface is slightly there is a bulge in this surface. There is a technical term for this, which elevated, right. So this is actually an elevation. A small elevation is what you can actually see here, right. If you imagine a potato being kept on a flat surface, and then you can, you know, measure this needle height and then actually jot down, you know, you make a 2D picture of that one, what you obtain is what people obtained when they actually created maps. So on the piece of surface that you have, which we will call as x and y axis, at different points you measure the height, and then let us say you connect all the points for whose height will be the same. So at different points might actually have same height, right. So if you connect all those points which have the same height, you end up obtaining what is called as a contour map, okay. So you can see that this is a contour map of a hill, because at the center, you know, the height would be maximum, and all these lines that I have drawn in this purple color correspond to a constant height, okay. And along this constant height, so this is the constant height map that I have drawn. So at different points on the x and y plane, so it's imagining like a potato kept on a flat surface, or a mountain that is kept on a flat surface, and then measure the height at different points by plunging the appropriate measuring tools and then calculating the height and then creating a contour, okay. Now let me show you something. Suppose I am at this particular point, okay, and there is a certain contour along this point, okay. What I do now here is, from this point I just, you know, imagine taking short steps, okay, by my stick or something. So I just imagine taking a short step along this. Now observe along this blue line, right, I am actually moving along the contour of a constant height. So let us say this height is equal to 40 meters, this height h is equal to 60 meters, and this height h is equal to some 80 meters, and this point let us say is equal to 100 meters. So you have a hill which is about 100 meters height, okay. So along this blue line I am actually moving on the contour itself. I have taken a short step and I have seen that there is no change in the function. That is because I am actually moving on the contour, right. If I move here I see some change but not much. If I move here I see some change but not much. But if I move perpendicular to this contour, right, so let me go back to this one. If I move perpendicular to the contour, then I experience maximum change, right. So from one surface to the other surface, if I move perpendicular, surface of constant heights or contour of constant height, I actually experience maximum change, okay. And this maximum change that I am going to obtain will be the change along the delta f. If I move on the same contour, of course I am not seeing any change in the height because these are the constant height contours. So from this you can imagine that, or you can observe that the gradient that you are going to find out will always point, it will be perpendicular to the constant f values, that is these are the contours of constant function values, and this would be the gradient which would always be perpendicular. And as you go from one contour to the other contour of or different values of f, if you keep moving along the gradient you will actually be able to reach the maximum point much faster than you take any other point, any other path. So if you were to move along this path, okay, then you would take longer time, because here as you move you do not see any height, and then as you move along here you see a maximum change of the function, and then as you keep moving along here and reach the point which is the top of the hill, you would have taken lot more time than what you would have taken. So this is the physical significance of gradient. Gradient always represents the maximum change, and in fact if you want to descend from the top of the hill, you have to just find out what is the maximum gradient or maximum slope and then descend in the opposite direction. This is called as the steepest descent, and it is one of the very useful signal processing operation that you are going to do, okay. So this completes our discussion on gradient. We will see couple of other operations that we are able to perform with the del operator in the next module. Thank you very much.